This video is on how thick is aluminum foil. And you may not care, but let me tell you why I was interested in this. I made a video on the largest water balloon you could make if you used all the water on the oceans. And I said, well, would wrapping a basketball in aluminum foil, is that the same proportion as the thickness of the ocean relative to planet Earth? Like, planet Earth is roughly 8,000 miles in diameter, and the average ocean depth is about 2 miles. So 2 miles over 8,000 miles would be like the fraction of the ocean over the planet. So I was wondering, is that a similar relationship with the aluminum foil? This thin layer of foil over a basketball. Basketball diameter is 9 inches. This one's a little old and deflated. I don't think it's quite that big. But a standard basketball is 9 inches in diameter. And so I was wondering, is the thickness of this aluminum about the same thing? So there's a couple of really nice mathematical things that come up in this analysis. So if we look really close at this aluminum, if I know that it tells you on the box the area of this, 75 square feet, and I measured this as 1 foot. So if the area is 75 square feet and this is 1 foot, that means the length is 75 feet. So if I were to straighten this out, it would be 75 feet long. And if we look at the little edge of this, it has a little bit of a thickness, and that's what we're trying to find, is that thickness. So if we straighten it out into a giant strip, we know that the area of this strip is going to be the length, 75 feet, times the width, and the width is what we don't know. But we can take that thing and coil it around this thing, and we get the same area. Whether this thing is straightened out or wrapped around, it has the same area. And I'm going to measure the diameter of the inner radius and the outer radius. And so we're left with this little ring. And so the area of a circle is pi r squared. So we can do that for the outer radius. And then subtract pi r squared of the inner radius, and that will give us the area of this thing. And then we can divide that by the length, and that gives us the width of the aluminum. Here's the explanation for how we calculate the width of the aluminum foil. It's so narrow that we can't just measure it with a ruler. We measure like lots and lots of layers of it and then calculate the width. So they tell you on the package that it's 75 square feet and the width of the roll is 1 foot. So we know the length is 75 feet. We're trying to calculate this width. So if you think of this as a rectangle, a really long, skinny rectangle, the area of that rectangle is the length times the width. And this little tiny narrow width is the thing we're trying to calculate. But if you take this area and you roll it up, you still get the same area. So we know the area of a circle is pi r squared, so it's the area of this outer circle minus the area of the inner circle. And so we can set these two areas equal to each other and solve for W, and we get this. And I measured the outer radius to be about 0.7 inches and the inner radius to be about 0.6 inches. And we divide by the length in inches, so we get 0.00045 inches. That's the width of the aluminum foil. But check out this other result. So we want to wrap this basketball in aluminum foil. So I cut this piece of aluminum foil so that it exactly wraps around the basketball. It has the right length, approximately. And I also cut it this way so that it's about 9 inches tall. So this outer thing is a cylinder. If this paper wasn't all crinkled, it would be a perfect cylinder with the same height as the sphere. And there's a beautiful mathematical result that says the surface area of this cylinder is exactly the same as the surface area of this sphere. So and I will show you how that proof goes. It's related to the video I made on sliced egg surface area, where you run an egg, you slice it this way, and all the horizontal strips have the same surface area. Clearly for this cylinder, if we were to cut this cylinder into strips of equal width, each strip would have the same area, but it's not so clear with a basketball, with a sphere, and I'll show you how that works. So the cool thing is I don't have to make this like conform. I know by this mathematical property that this cylindrical surface area is the same as the surface area of the basketball. Here's the proof that the area of the surface area of the surrounding cylinder has exactly the same surface area as the sphere. So here, this sphere is being revolved around this axis. So you take this red surface area and you revolve it around like that. And so clearly, if you have a cylinder and you cut the cylinder into equal width slabs, obviously each one of those has exactly the same surface area, and the same property holds for the sphere. So the trade-off of this length and the width trade off exactly in the right way such that their product is constant. So when you're down here, it looks kind of like the strip of a cylinder. It's just kind of like the radius times the height of this thing. And then as you get closer and closer higher, the radius shrinks and the width of this thing gets bigger. So if you look at the geometry of that, say we're at angle theta, the radius at that point is r cosine theta, but the length of this little arc here, ds, you have to divide by cosine theta. So that's theta, so that's theta. The radius is tangent to the circle, so that's a right angle, so that's 90 minus theta, so that has to be theta. So just using the definition of cosine, this little piece is dh over cosine theta. So the area of the strip, the cosine theta here and the 1 over cosine theta here cancel out, and you just get r times dh. And so each one of these little strips has exactly the same area, which is the same area as the cylinder around it. So so the water balloon thing says, okay, this represents the water on the planet, even though only about 70% of the planet is water, but we'll just suppose the whole planet was covered in water. And then if we were to crumple that up into a water balloon, this gives us some approximate size of what is the largest water balloon we could make, relative to the planet. And of course I could squish this a little bit more, so there's some error in how much we squish this. But this is sort of the right kind of scales and sizes. Okay, so let's tie this back to the original question. How does the aluminum foil thickness compared to the diameter of a basketball compare with the average ocean depth relative to the diameter of the Earth? So the average ocean depth is about 2 miles. The diameter of the Earth is about 8,000 miles. So that gives us a ratio of 0.00025. We calculated the aluminum foil thickness to be this. The diameter of a basketball is 9 inches, so we get this. So the aluminum foil is too thin by about a factor of 5. If you have 5 layers of aluminum foil, then it's the same as the ocean over the planet. So now I understand why my friend Rich asked me, was I using regular aluminum foil or heavy-duty aluminum foil? I told him that I was using regular aluminum foil, and he said heavy-duty aluminum foil was much more interesting, so I should have taken his advice, because probably he could see this all coming. He probably knew that a heavy-duty aluminum foil would have matched perfectly. I mean, Rich is really smart. If you look at Google Trends of regular aluminum foil in blue versus heavy-duty aluminum foil in red, we see the heavy-duty is much more popular. In fact, in July 12th to July 18th, 100% of Google searches were for heavy-duty aluminum foil. So just one more time, he was right. I should have listened to him, to what he was saying. So that means if we were going to use regular aluminum foil, would need a ball that was about 5 times less in diameter. So a golf ball has 1.6 inches. We needed something about 1.8. So it's about the size of a golf ball. So if we wrapped a golf ball in regular aluminum foil, But it just doesn't make any sense to wrap a golf ball in aluminum foil. It makes a lot more sense to wrap a basketball in aluminum foil, because if you look at like basketball, you know, they're pretty much anti-correlate with each other. Like basketball is getting much more popular, and when basketball is popular, or whoops, golf isn't. They're kind of anti-correlated with each other. And look at red is golf. Golf is kind of going down, and basketball is going up. Like 100% of Google searches are for basketball nowadays. So I guess we'd have to wrap the basketball with heavy duty aluminum foil and wrap the golf ball with regular aluminum foil. And I think also like that's why it chose these colors like red. I think more Republicans play golf and more Democrats play basketball. And like it's showing the states by like presidential election, like, oh, the red states. They got California as a red state. Interesting. And then all the other states like are voting for basketball. Well, I guess we learned something about the thickness of aluminum foil, and clearly heavy duty aluminum foil is much more popular than regular aluminum foil. So I should have done what my friend Rich said. And thank you very much. And thank you very much.